Thank you, and same to you.
Okay, thanks. Okay, so few people today, but I'll get started. And I'm swapping the class today with Janendra because he has some urgencies. So today I'll run the class in a hybrid mode. So I'll be playing some pre-recorded lectures of myself, and I'll sit back, and you can raise your hands or unmute yourself and ask me questions if you have um, if you have any. So it is going to be pretty simple, not technical today. I think it's more about introductory sides of the data mining algorithms, and all will start from the next class onward. Okay, thank you. So let me share my screen, and let me play the video. It's a recorded lecture on the iPad, and let me know if you have any difficulty in seeing.
We can see a screen, but it seems I think you're yet to start. Can't hear anything.
There is no audio.
Sir, video is playing, but we can't hear anything. I see the seconds are increasing, but no sound.
Hi guys, are you able to see and listen to the lecture, or is there any technical difficulty?
We were able to see the video playing, but we can't hear anything.
You can't hear anything. Okay, so
Yeah.
let me
I mean, I can hear you right now, but video sound was not.
got it, got it, got it. Wait a second. I'll just manage. Just a second. So now let me know. I think that's why I just wanted to check if everything is all right. Compared to, can you hear now? Interval. Okay, so
Yes,
let's
it's audible now.
which can be performed on the each types of the variables. So the excellent. Okay. Okay. So now let us look at. I think if you have any question about the different variable types, just let me know. If you have, I mean, it could be slightly confusing to understand what is an interval, what is a ratio, but with the example of the salary, I think it should be clear in your mind. The same set of things can be explained as both ratio variable and interval variable. Is your choice. Sometimes it makes more sense to consider ratio as compared to interval. Okay, so let's see some operations which can be performed on the each types of the variables. So the first thing is distinctness, which means that you can differentiate between two things. Now, distinctness should be there. You should be able to say that, okay, this value is different from eye color is blue, is different from eye color is gray, right? So that is the distinction. And that distinction is there in every type of variable. Without it, it doesn't make any sense to present it to the machine learning method. Order, orders are sometimes implicitly there. Like I told you about the grades, like the grading in the exam. You have the order A, B, C, D, E, F. Now they have implicit ordering, and you know that which grade is better than which grade. Okay, differences are meaningful. So these are the properties. Not that all types of attributes will have all these four properties, but we'll see what are these properties first. Differences means you can subtract or add and you can still make sense, right? Ratio means you can divide and you can still make sense. Now, looking at the nominal variable, the distinctness is of course there. Ordinal variable, distinctness and order both are there, right? You can distinguish between grade A and grade B, and you can order them as well. Nominal attributes like eye color, you cannot order them, right? So distinctness is there, but ordering is not possible. And neither you can do differences. You cannot subtract blue from black, right? Do ratio either. Ordinal attribute, you can do distinctness, you can do order, but you cannot do differences necessarily. Okay. Why I'm saying so? Like grade A and grade B, the difference of these two things may not make much sense. We don't do that. We don't say that, I got X% more grade as compared to you. So grade is calculated differently, and we don't typically understand what is the meaning of the differences between pairs of grades. Okay, it is not straightforward. So we don't consider that to be a variable where difference could be applicable. I hope that is clear. Interval attributes, of course, distinctness is there. You can distinguish between, two interval variables, like the differences between a pair of people's salaries, right? And, multiple entries, like how much you earn more as compared to your friend. And so that's a relative thing, but you still can distinguish between two entries, right? Like I earn 50,000 more, you earn 70,000 more than some standard, and that you can consider to be comparable, that are distinct, in fact. Order, yes, you can order them because they have numerical interpretation, so they carry order numerical. Sorry, since you can interpret them numerically, you can order them. Meaningful differences are actually meaningful, right? You can find difference between two values because that's the whole purpose. So differences work in values which are interval attributes, which are of the interval kind of attribute. And all these four properties are actually, so ratio is the most I think all-encompassing thing where you can apply all these operations. I think so far it is pretty much dry knowledge. We'll see more examples as we go forward. Again, I think this is pretty much rehashing of what I just said, so you can just go through this later on at your own pace. Okay, these are the two categories of all this, types of attributes that I just spoke of, right? The discrete attributes and the continuous attributes, and they need different kinds of treatment. Okay, so you know what is discrete, like zip code. You cannot give a zip code like 0.110020.5, right? That cannot be a zip code. So zip code are finite set of numbers, and you cannot choose a number in between. So that's the discrete attribute, right? Counts, for example, you cannot have intermediate values. Like there are certain things. For instance, your stock in the inventory, right? For a particular items, you can have a count. You cannot have like this point, this, right? So that is not acceptable. So likewise, this is a discrete value, right? And even nominal values are discrete. Is there any question so far?
So there was a question, a request for starting the recording of this lecture.
It's fine. It's the recording. It is a recorded lecture, right? I'll share the recording directly. I need not record this thing.
Yes,
Okay.
sir. Right.
Okay.
Okay.
Thank you. Discrete variables, like a set of words in a collection of documents. These are all. Actually, what I'll do is I'll just speed it up a little bit, guys, because I really want to cover 2 lectures today, so that I can start with the algorithms from the next class. Data mining algorithms. Is that okay, or do you think it is already going too fast? We can just make it slightly faster, right? Let's see. All discrete things. These are very simple things. So not necessarily the discrete ones should be the integers, right? Like the eye color could also be a discrete attribute, right? Because there are only finite number of possibilities. Okay. Guys, one more request is I cannot see who is raising the hands and all. So please speak up, right? And I'm sitting here all time, so I'll answer your question. Binary attributes are a special case of discrete attributes, like male and female. You might represent that using a binary variable, so that becomes a binary attribute. That is also discrete, right? In fact, if something has a class grade, all the grades are discrete values, right? So these are different examples of the discrete programs. Continuous attributes, you understand, temperature can vary, continuously in a spectrum of values, right? Not necessarily the negative values, but yes, negative also is possible, right? With very small possibility. Very small probability you can go to any temperature, right? So you can probably consider that as a very good example of continuous variable. Height, you cannot go to negative, but you can have positive heights. You can explain it with some distribution which does not like normal ones. Normal distribution or Gaussian distribution might, or Poisson distribution or binomial, all these things can be used for explaining positive values, right? So these are continuous attributes. It can take any value whatsoever, but of course within a logical range. And we should understand, we'll see at the time of exploratory data analysis, that how to look at a variable and its statistical properties, including the distribution. That's a very, very important key thing to do as part of the exploratory data analysis. Okay. I think we can skip some of this. These are, yeah. Okay, guys, I'll just stop here for a minute, and before it goes out of my mind, just let me tell you, there are 2 very good books that you should um, uh, either buy or borrow from the library. Okay. The reason I'm saying you should buy is these two books are really easy to understand. This may solve a lot of your data science queries very easily. It's easy to go through. Okay. So number one is Vipin Kumar's Introduction to Data Mining. And number two is again some introduction to data mining by Han and Camber. Please write it down, Han and Camber. And Han and Camber book, if you ask our librarian, he can give you a soft copy. But it's also good for you to buy this and keep it in your collection. And Vipin Kumar, okay? If you go through these two books, you will be a very good data scientist and data mining guy. And it also explains a lot of machine learning algorithms in a very lucid fashion as well. So it is a must collect book. Both these books are. And the slides that I'm showing, at least in this particular class, have been taken from Vipin Kumar's lecture website, right? Vipin Kumar, the book has a website, and there will find a lot of slides. So these slides have been taken from that place because those are quite wonderful. Sorry for the break. Go on. So let us jump onto the next part of the lecture, which is the data, important characteristics of the data. So what we should be careful about at the time of analysis of some layer data is this dimensionality, which means the number of attributes, the number of data points, both are very critical. You know, there is one thing that we typically don't study as part of data science is, algorithms. Because algorithms give you some sense of, I don't know how many of you are from computer science, but you will recognize that when you implement certain algorithm or certain machine learning method, you really need to be careful and cognizant about its time complexity, right? Because even if it works very well, it turns out that many cases the algorithms are extremely slow, right? Can we use real-time, convolutional neural network on a large data? No, because it takes a lot of time to train, right? So you should understand the time complexity of the various machine learning methods. Try to give a little bit of extra effort to figure out what are the time complexities and when, in what context it is useful, in what context it is not. Typically speaking, you don't care too much about time complexity in machine learning. The reason is that you train a model and then you use it. You don't train on the go. But if you train on the go, if you do online machine learning, guys, just two questions trivia for you. Number one, can somebody tell me what is ordinality and give an example of ordinal variable?
Rank, rank of students.
Sorry, guys, tell me. Somebody is just trying to answer the question.
Sir, rank of students for ordinal.
Ordinal is when
Rank of student, yes.
we have categories and the order of the categories also matters. For example, low, medium, high.
Correct. So it's very interesting, right? The temperature, low, medium, high, all these examples that you guys have given are correct. So now think about their usage in the data mining, right? In the machine learning, right? So you can, it's a string, right? When I say high, low, and medium, right? If I say temperature, high, low, medium, that's strings basically. Those are strings, right? Those are not numerical values per se, but they have ordinality that you can exploit. Ordinality means they have an implicit order, like high is higher than medium, medium is higher than low, right? And therefore you can actually numerically code them to extract maximum out of it. So if you treat them completely like a string in your machine learning task, then you will lose on a lot of good information. That is their relative strength. So that is ordinality. The second thing is, can somebody tell me what is interval variable and give an example from the life? It's a bit noisy on my side. Please excuse me. Yeah.
Maybe same as ordinal, but the distance between each of the category is defined and same.
Yeah. So just an example, can you
Uh,
like, yeah, tell me.
could be three different salaries for three different
Exactly.
people or
No, not three different salaries, salary
levels.
ranges. For example, tax slab, income tax slab,
Right.
right? Where you have an interval, like if your salary is under 6 lakhs or below, then this is the tax, and 6 lakhs and 10 lakhs is. So in this way, interval variables are very common in the survey data, right? So remember these two things, and they also have a pseudo implicit ordinality. The reason I'm stressing on these things is we spend a lot of our time and energy in data science courses on learning mathematical techniques, but these are practical things that you'll have to know, that and therefore whenever given a problem, you'll have to first look at the different types of the what are the different types of the variables, and it might not come to you in a machine learning amicable way. So you'll have to modify it, you'll have to impose ordinality, you'll have to code it in a manner so that it makes sense, and so on and so forth. There is a lot of common sense that is involved in data science more than this techniques, because techniques are available through APIs most of the time. Okay, so carry on, guys. Thank you. For instance, then you should have a mechanism by which you can learn very fast as the streaming data hits your database. I know Microsoft was working on a lot of online machine learning problems a few years back, and they developed methods for accurate and fast learning online. That means as you receive data, you train your model, you recalibrate your model, and you make it available for the consumption. Right. So in those cases, it has to be very rapid. You cannot. You can probably recalibrate your existing model instead of start the training from the scratch, right? For example, if you have an autoencoder trained on a very large data and some new data comes on your way, you may not just train the entire autoencoder from the scratch. You can simply, repurpose it or recalibrate it. You can tweak the weights a little bit in order for it to be more apt to the newly observed data sets, right? Um, so the data, the sample point, the sample size, that means the number of data points, the number of attributes, all these things actually add complexity to your, you know, trainability, or your ability to model the data. All right. Apart from that, there are other technicalities, involved in this, because if you have too many attributes but too little data points, it becomes extremely tricky to make any sense out of it. Okay. If you have too few data points as compared to, let's say you have 5,000 variables but only 100 samples, and let's say two classes. Now, in such cases, it's notoriously challenging to do the feature selection so that you get a very good accuracy for the classification, right? It's considerably difficult. So one has to know the dimensions well, and one has to, depending on the dimension, pick up the right machine learning method to apply. And that is the essence of dimensionality and your cognizance about it. As part of the data mining course, we'll teach like 2 to 3 dimension reduction methods and feature selection methods, and see how it simplifies your life. Data sparsity, I think in mathematics and optimization, you might have been taught sparse models, right? And what kind of, I don't know whether you have been taught, it is more like a mathematics course. It was not an applied machine learning course. But data sparsity is another big issue. For example, I work in the fields of biomedical data mining. I work on single cell data, to be more precise, where there are a lot of zero expression values, which is not the case when we use bulk RNA sequencing, right? So the matrix is full of dropouts, full of zeros. When you have too many zeros, that indicates that the data is noisy. You have a lot of missing values, right? And therefore, it needs special treatment, right? And the spatial treatment can come in any way, like through changing the distribution, underlying assumptions on the statistical distribution. You may change the method altogether. You can select features. You can do matrix completion. There are many, many things. I mean, it's an ocean of techniques that are available to fight sparsity in the data. Okay. I don't know what they mean by resolution, so I'll just skip that. Size, of course, matters. I think we discussed that as part of the dimensionality. I don't think that's a separate concept either. Dimensionality along the features or along the data points, both are equally important. All right, now let us see what are the different types of data. Okay, so the most common form of data is data matrix, which we use for machine learning data mining, right? But most of the time, it is hard to acquire the matrix. Tabulating the data is not straightforward all the time. So we'll see what are the other data types that exist, right? So data matrix fall under record. So you are recording something. For example, you are recording the patient details, the clinical history of the patient and the drugs, right? So that is the tabulation part, right? So typically in such cases, you come up with a fixed set of attributes for everybody, right? And you can put it in a data matrix. Document data, again, documents are part of records, right? It's a record keeping, but it's a text data. It is very different from the matrix. To convert it into a matrix, you will need to do a lot of transformations. Like to be able to learn from the document data or discourses, you need different kind of data treatments, okay? I think part of that you'll also learn in the NLP course. Transaction data, for example, you are running a supermarket and there are 10,000 people accessing your Walmart store, and then you accumulate transactional data like what are the goods or what are the articles purchased by a particular individual. If you have his tracking ID, then you can in fact keep a track of his buying behavior and you can make use of that. So that is the transactional data. That what are the goods that you took, what is the payment that you made, right? Graph is a very, very special kind of data. I'm sure in NLP, in one of the other classes, you'll be studying the social network, right? So graph is a mathematical structure, which is, which is very popular for representing interconnected data. Just give me a second. Right, so that can be represented as a graph. Molecular structure, like a molecule, has different atoms in it and different connectivities of the atoms that describe a molecule. So you can represent a molecule as a graph as well. Ordered, spatial data, temporal data, sequential data, genetic sequence data, all these things have some or the other kind of ordering. So this is an example of a record data, which captures the details of individuals, their refund status, marital status, taxable income, etc., and some classification, cheat, no cheat. Again, this is a data matrix, which is pretty similar to what I saw in the next last slide, right? Document data type, very interesting, because document data, it depends on you that how you want to process the document. Just give me a minute, I'll just grab some water. If you have question, you can ask me. I'll come back in 1 minute. Yeah, so document data, there are, first of all, do you have any questions so far? Let us please discuss.
So I have one doubt. So I'm not able to understand between document data and data matrix. They both look kind of same.
Yeah, that's a good point. Yeah, so I was coming to that. See, a data matrix. So guys, do you have the same question that what is the difference between a document data and a data matrix? So let me just go back to this particular slide where we showed the data types. So it is very important to understand the type of the data. You know why? Because most of the time when scientists come up with new algorithms, they come up with algorithm for a particular kind of a data, right? The algorithm that works on graph data will not work on the sequence data. The algorithm that works on the records, data matrices will not work on the other two types of the data. And that's almost always true. At least in my experience, I have not seen that the same algorithm works on the three data types. It cannot. By the nature of it, it can't. Okay. So therefore, what happens is when you identify if you know that what is your data type, you can actually find out what algorithms will be the right algorithms. Okay. So for example, all the graph algorithms, like community detection, one big problem in graph theory and data mining is that graph data mining is that you need to find communities or the clusters from a network, right, or a graph. So graph and network are the same. Okay, complex networks where millions of nodes will be there and edges will be there, and you will have to find the closely knit groups in the social network, for example. And when you know that, okay, this is my data type, you can use all the algorithms that apply to the data type to do your analysis. Okay, so graph mining is a advanced topic. If we get time, we can learn a little bit about graph mining. You can check out my paper on overlapping cluster detection from large graphs. So that's one of the state of the art. And record data is the most common data that you will deal with in machine learning classes as well, where you are given with the tabular data. It's actually most prevalent data as well. So matrices, normally for most of the problems, simple problems, we get data matrix for the classification, for the clustering, and all this 90% of the algorithms that we'll learn in the data mining or the other classes, other courses here, are applicable to the data matrices. Transaction data needs, again, so transaction data is slightly different from the data matrix, because in transaction data you'll have to look at problems such as frequent pattern mining and stuff like that. Okay, so we'll learn about all those algorithms as well. So this classification or categorization is actually depending on the source of the data. Is it a record keeping kind of an exercise, or it is a graph social network, or it's ordered data like things are happening periodically or along the time axis? Okay, so this is very interesting. I think you might know that in deep learning you have methods such as recurrent neural network and LSTM, or you can use even classical methods such as Markov chains for modeling sequence data. It's very advanced and interesting. So we'll just move forward. Document data is, see, document is a text document, for example. That's not like table, but you can actually tabulate it for your machine learning purposes, right? You can take a document and you can count the number of times the words in the dictionary appear, right? And depending on that, you can create a vector representation of the document. And this representation used to be a very clever way of representing the documents and doing machine learning, because all the machine learning algorithms, such as clustering algorithms, are straightforwardly applicable on this kind of a data. You are simply keeping a track of how many times a particular word occurred. Okay, and you can imagine if you measure the cosine distance between these two vectors, right? Any two documents, tabulate it like that and look at the cosine similarity vector, right? And between the vectors, and then you can use this cosine similarity as a distance to do the clustering. Okay, so this is one way you can represent the document data, but it is unfair to say this is the only way the document can be represented. So today, most of the algorithms take simple text data, right? And for example, word2vec and all these NLP based methods you learn in the next SEM are based on this. Okay, are based on a normal document, the text document without any tabularization like this. Of the document. This is not the document itself. A simple method could be you take learning methods in which you learn the word representations, which you learn again in the NLP. You can learn word representation
using.
I think we have covered
one
this,
should
so I'm
first
just
ask
moving
that what-
on.
Yes, sir. Thank you, sir. This is an example of a transaction data, like the transaction ID and the transaction items, the items which were purchased, etc. And you can see how it looks like. And transaction data, one should first ask that what are the typical tasks that you can do with transaction data. On the transaction data, one very important task is to do association rule mining, right? Where you try to find that whether a person, when he buys bread, whether he buys Coke as well or milk as well, right? So this kind of relationship, like, frequent patterns, I would say, in other words, which we look for in the transactional data. And that is extremely, extremely insightful. I mean, in departmental stores, the transaction data are used to design your shop floor and decide that where to keep what. And just by placing things at the right place, you can actually increase your revenue significantly. And the transactional data could also be more structured. For example, here you have different number of items depending on who bought what. But I am saying it's also possible that the transactional data is pretty structured. And one example is your banking transaction, like your ATM transaction or one particular NEFT that you do. So that preserves all the same. If you go to your HDFC bank account, you see this is the tabulation. Each one of my transactions is tabulated in a very structured manner, every time having the same set of attributes mentioned over there, right? So that is your transactional data, but that is structured. So transactional data may not always be tabular. It could be tabular. It could be simply transactional also, right? So although these are the different types of names given to things, just to help you understand what are the different data types and what all avatars data come to you. Like if you get a tabular data, it is the easiest thing to deal with. You can simply use any clustering or classification or regression algorithm depending on the problem type, and you can start with the predictions. Whereas on transactional data, you cannot straightforwardly learn run any machine learning method, right? You will have to do stuff like association rule mining, like frequent pattern mining, stuff like that, which are slightly different algorithms from this. All right, graphical data again is very frequently observed in different fields. Things are connected to each other. Social network is a great example of graphical data. Bibliographic network is another example where depending on for example, this is a document where this particular document is referred to or cited, and then this particular document cites this document and this document, etc., etc. Right? So these are bibliographic, this is a bibliographic network where you have the nodes. So each item is a node and they have edges, right? The nodes have edges in between connecting them. And the edges could be directed, right? For example, this document refers to this document. That means there is a direction from this document to that document. So in this kind of data, again, it is not straightforward to run machine learning algorithms like classification and clustering, but you need special kinds of algorithms and data mining techniques to deal with graphical data, network data, in other words. So graph data, when you say graph, it might also sound like, are you drawing some graph or something? It's not like that, so don't mix up chart and graph, right? Graph in mathematical term, in a discrete mathematics terminology, graph means a network, right? Where you have certain entities and their connections. But it turns out that machine learning is not directly applicable on this kind of data. Ordered data, sequential data, right? Where you have a particular sequence in which things are given to you, it is not tabular. This data is not tabular. This is the DNA sequence, right? As you know, our DNA consists of 3 billion bases. So it's a very, very, very long list of nucleotides in a particular sequence. And you cannot really play with the sequence because this is predetermined, and a change in the sequence will typically cause a death, right? So this is a very stable kind of a sequence data. And there are methods like In the deep learning also you have recurrent neural network, LSTM, all these things which deal with sequence data, right? So there are different machine learning methods which can directly take input from sequential data like this. You should, I think in the next trimester, the deep learning classes, you will learn about how to deal with sequential data. You can do machine learning with the sequential data. You just need the sophisticated methods to do that. Okay, so machine learning can be done both on the sequential and as well as tabular data. So yeah, again, this is a spatial temporal data, which is another, you can think of it as an ordered data. That means, there is a sense of direction. There is a sense of how the temperature is changing over the time. So, and over the space, right? So, all these things are can be considered by loose sense as ordered data. But spatial temporal data is a special kind of data altogether, right? Very special. And there are multiple companies like, look at this. Just check out this company. It's called Discrete Lab. Okay, so what they do geospatial data mining, and they give a lot of intelligence based on that. In India also there is a company to analyze geospatial data. Mineral exploration, infrastructure detection, land conversion, monitoring, property attribute development, weather forecasting, crop health and yield. Wonderful applications, right? So this company works on geospatial data to make predictions on all these things. I don't have any experience in handling geospatial data, to be frank. A lot of these econometric guys, I'm sure Gaurav Arora, for example, works on geospatial data. You might get in touch with him. I remember he's speaking of that. Okay, now let us come to the data quality issues, right? So data quality is a very big problem, simply because, whatever you see on the internet is not completely reliable. Neither if you get something from some other sources, it is reliable, right? So the reliability of the data is something that you will have to understand as a domain guy, right? You will have to, I can tell you from the biomedical genomics point of view, like we get sequencing data from next generation sequencing platforms like Lumina. We take the cells and the tissue and subject it to sequencing, and the sequencing machine will typically give rise to a lot of errors, right? The machines are not perfect, and those errors will somehow distort the signal in your data, right? So you have to be cognizant of that, and you'll have to have mean mathematical and statistical ways to deal with that, right? So noise and outliers are almost there in every data, right? You don't know the complete sanctity of the data, unless you are a domain guy. So you'll have to talk to the people from that domain to understand what are the different sources of noise that one should worry about. Yeah, so there are misleading data entries in many cases where you cannot again completely rely on that. Fake data, there are a lot of, I'll give you a very good example. Like if you are doing trading, right? There are a lot of YouTube channels which every time tells you like, this is if you are an intraday trader, why don't you buy shares of this company tomorrow, and you will. Now let's say you are using NLP to look at thousands of websites for which tells you that which share to buy tomorrow and which not to buy. Now, if you're not an expert of the field, you will typically rely on trust on them, and what you'll do is you will, put your money in the company. So that's the fake data, which can totally mislead. For example, Twitter. There are companies who manipulate through tweets, through articles, and they create a sense that this company is in a very good shape. right? A few days back, you might have heard that Jet Airways said that they are starting their operation. But when you dig out more into it, you will see that there is no real, the source of the news is not very reliable necessarily. So fake data is very, very prevalent, right? And one should be extremely careful before subjecting it to machine learning. The machine learning is what your data is, right? It cannot be better than your data. So garbage in, garbage out. Missing values, again, very, very, very prevalent. Uh, a lot of times you make entries, like in hospital, if you are entering details of the patient, and then the patient you are tracking, and he goes out of track, something happens, he goes out of contact, then you have a missing entry in your database, right? And machine learning algorithm, not that all machine learning algorithms can handle missing entries. Data duplication is another problem. You'll have to remove the duplicates very carefully. Otherwise, it will inflate or deflate your accuracy, and you will think it will be completely misled if you have too many duplicates in your data. So here is an example of how noise distorts the data signal. You have two sinusoidal waves here, and the black one and the red one, and they are with different frequencies. And but you don't see them separately, right? You get a combined kind of a signal like this, right? Like audio of a song. The voice and the percussion, the synthesizer, all these things come together, right? So they come as a consensus signal into your ears, and then you perceive it as a good music or bad music, right? So that you can think of as a noise. So noise is indistinguishable from the data, from the signal, right? It distorts the signal, and you see this kind of wiggliness, right? So there are many methods by which you can process the signal. For example, Anshul is a very good researcher in the field of signal processing, right? So you can talk to him if you are more interested. So noise cancellation, signal processing are important topics as well, to tease out the noise from the data. Existence of outliers, we have discussed this already. I think a lot of times you don't want to. I'll give you a very quick example. Like, probably you know how the principal component analysis works. If not, then what it does is it finds out the direction of your maximum variability in the data. So principal component analysis is a dimension reduction method. It basically looks at your data in a multidimensional space, and it tries to figure out what is the direction in which the data is varying the most. Now remember, if you have this kind of outliers, they will create a sense that there is a huge variation in this direction. If you look at this data, the data variation is actually in this direction more than this direction, for example. But because of this outliers, it will look like the data varies most along this direction. So if you have an extreme outlier, that will dominate, influence your overall outcome of dimension reduction or clustering or classification. So a lot of times you identify the outliers and you remove it. A lot of times the outliers are ones which are very important for you, like network intrusion. How will you detect network intrusion, right? How will you detect a credit card fraud? Because something outlierish, like if you have seen that from your bank, there are 5 consecutive transactions of weird amounts, right? I mean, nowadays you might have seen this, series Jamtara or something, right, in Netflix. So this is very prevalent, right? It's a multi-billion, $18 billion industry in India. This fraud, right? So can you create algorithm which can catch fraud very easily, depending on a lot of attributes, like when, at what point of time the transaction is made. I myself have been cheated online. I lost 80,000 rupees like last year, last to last year, right? And you trust me that what this guy did was he hacked my phone. He took 10,000, 20,000 rupees at a time, multiple transactions. Before I could do anything, my bank balance was wiped out completely, right? Thankfully, I had very less money in that account, so I got relieved. But otherwise, there are cases where 60 to 70 lakhs to 1 crore got wiped out very quickly. So can you But you can imagine when a transaction is taking place, so many things are being tracked, right? So many information pointers are getting accumulated. So can you look at it and stop the such fraudulent transactions? Is a $1 billion problem in our country at least, or elsewhere also. I mean, so that's the use case of outlier detection. Missing value I have just discussed. We'll see more how to handle the missing values in later classes. Okay, I think I'll stop here. I'll take a few questions, and Krishan has already floated the link. You guys can go and join. I'll continue from the. I think we have already covered the introductory part of the data mining. From the following classes, we'll do some real mathematics and algorithms and practice. Any question? Happy to answer. All right. So I don't think there's any question. So why don't you join Krishan's link and continue with the hands-on? Thank you, guys. Thanks.
Thanks.
Okay, now guys, is there any question at this point? Just let me know. We'll switch to the other presentation. It's pretty straightforward, self-explanatory mostly in nature. Good to take questions. Guys, is there any question? Just let me know. We'll switch to the next presentation otherwise. The previous one is very simple. What are the different data types and what are the different kinds of variables? That's it, nothing else. Some examples of data and some idea about the noise that you accrue. So this is the next presentation. This one is more whiteboard work, so you'll have to pay a little bit of attention. Again, just let me know if you have any confusion. I'm here all through. So just let me. So just let me know if you can hear and listen to it, see this.
So anyway, so last time we talked about data, right?
Guys, is it audible and visible?
Yes, sir.
Data and different types of attributes primarily. Okay, and yeah, a little bit about what kind of problems, right? Problems with the data, right? And it's either very thick or it's very thin. Okay, so among the, sorry, yeah, okay. So among the major problems with the data, the first thing that we encountered was noise, right? So noise is a major problem, and the noise comes from recording of the data also, right? So, for instance, I was involved in one of the consortia to help Niti Aayog. I don't know whether you have heard of this organization called Brookings. So it's a think tank. So I was involved with them in helping the policymakers in our country for health policies, right? And so we are working on National Family Health Survey data, the fourth version, and and we realize that there's a lot of noise in the way the data is recorded, right? Because you can imagine it's a huge this service, the countrywide service are very large efforts involving millions of dollars, if not billions, and then many people are recruited and they reach out each and every household, at least ideally, and then the way the data is recorded is sometimes questionable, right? So we never know because nobody asked me about the family health, right? However, it represents the entire country, so it should be a very large sample. But but you can imagine how this data is recorded because there are a lot of fields in each of these forms. There are about 100 fields, right? And then somebody take a note of all this information, and then this information. So information capture, at the time of capturing the information, you make a lot of errors at the time of digitize digitization. You again introduce some errors and so on and so forth. You can think of multiple ways in which error can creep in, right, into your data that finally you receive for doing data mining, machine learning, stuff like that. The other kind of stuff that I have often seen while working with, I mean, all these things I'm telling you from my personal experience, right? So you can probably, there is no rocket science. You should always find out ways to deal with the data. It's not a showstopper. But what we have also seen is that in Indian hospitals, right? They use, for example, if somebody has a comorbidity, just as an example, right? Like every patient that is admitted in your hospital, right? You'll have to create, at least in AIMS, they have a very large hospital management system, and they record information for all of their patients, right? With their clinical data, the lab reports, blah, blah, blah. So it's a very, very large um, rational database system, the RDBMS, right? And it turns out that they pretty much make freehand entries, right, for a lot of fields where you should have prefixed values, right? So let's say some disease name, they have 5 to 6 different ways of writing the disease names. It's not coming from the drop down, right? So the more you let the user write of his own, the more noise you introduce to the data, right? And then it becomes a nightmare to sort of figuring out that, for example, you are performing a procedure, right? Let's say, a stent on the heart, right? So they have different nomenclature, and all of these things refer to the same thing. However, the way that information is captured often gives rise to multiple different synonymous strings. None of them is wrong. It's just that they're the same, and yet you consider them to be different, right? So those kind of problems are also very, very prevalent in at least in our country. I have come across these kind of things, and I'm sure there are elsewhere also will have similar kind of a problem. Now, of course, this is where the noise comes. I can give you one more example because, as I told you, right, I mean, when we take the cell, a cell, and it has a DNA, we subject it to sequencer, right? It's a big industry, by the way. And then you get to read the DNA, RNA sequences, right? Nucleotide sequences. So the sequencer has its own errors, right? Because the way this entire chemistry happens introduces a lot of different errors, and it's very difficult to spot all of them in the first place. So yeah, so we'll have to be cognizant that such errors can occur. You may not know exactly the distribution of the noise because statistically speaking, to tackle the noise in your data, you should ideally know the distribution of the noise. But there is nothing. I mean, there is no theoretical distribution that is known for most of your data, right? But in some cases, you might know, or you can guess, or you can plot, and you can decide, right? So it's nothing very definitive, here. So these are some of the, and of course you'll have, I don't know what this, how can I move this figure down? So let me just, okay, anyway, the other problem that we'll see is of duplicate data points. We discussed that last time. Duplicate records, I would say. And sometimes it's straightforward to just get rid of the duplicate records. Otherwise, they just inflate or deflate your the performance of your classifier, right? So sometimes the duplicate records. I mean, if you have an ID, right, like ID, and then attribute 1, attribute 2, attribute 3, and then you have ID X here, another X here. That is a duplicate, right? Your IDs should not be repeated. However, the data points can match by chance depending on the nature of the data, right? So you have to be cognizant of whether there is an ID repetition, right? In that case, you'll have to get rid of one of the records or understand how that cropped up in the data. Okay. Among the rest of the problems, one major problem is of course of missing values, right? And you know what is the missing value, because a lot of times you don't record, the entire. For example, when you fill up any form, and the form is very big, right? Typically, you tend to just fill a small number of fields, right, in the form, and not the entire thing. And so is done by the rest of the people as well. So it turns out that only a very tiny number of fields which are common across, which are mandatory, are only filled, the rest are not, in which case you of course give rise to a lot of disparity among your data points, and you need to know if there are too many missing values for a particular attribute or for a particular record, then you should treat that accordingly. Okay, so that's the idea of the missing value. We'll learn more about that as we go forward today. All right, and finally outliers. And what I thought today is to get a bit warm with methods. I think let's get started with one outlier detection method today. Of course, we'll get back to it in some of the next classes, but just to break out of the monotonicity, right, of theory. Let's get into some algorithm and see how it works. So outliers are data points which, for some reason, it could be a genuine reason, or it could be something mischievous, but some data points are outliers, and they distort a lot of your unsupervised analysis a lot. So typically, supervisory analysis are still robust to outliers as long as they are not too many in number. But in unsupervised method like dimension reduction, outliers actually influence a lot, right? Now the point is, how do you detect this outlier? Yeah, something could be rare. For example, these 3 dots, they still create a cluster. They are not as big as this cluster, but they are still a cluster. So they are rare, but they are not outliers. Outliers is something far off from any of the center of gravity of the data, or any structure that the data has, and it sort of gives rise to problems at the time of feature extraction, stuff like that. So we came up with the extremely rapid outlier detection method. It's called FIRE, and FIRE, right? Finder of this abbreviation for finder of rare entity. It's a patent pending algorithm. However, the paper is published. Please check out this paper in Nature Communication from my group, Jindal et al. 2018 Nature Com. So this is currently the fastest algorithm for outlier detection and the best performing. So, and with it, we could discover a potentially new brain cell type. So we showed application of the brain cells. So far, any question? Anybody? All fine. Thank you. Thank you.
Sir, I have a question.
Yeah, go ahead.
Sir, for the missing value case, I want to ask how to deal with the missing value, because there are factors like replacing the missing value if we have a factorial data set by mod value, or by if we have a numerical data set, then we have to deal with mean and median. But if we deal with like replacing a value by mean, median, or mode, can't it introduce the biasness in the data set? Because replacing the maximum values, missing value with the maximum occurring value in the data set, then it will bias the feature of a data set. Is it right to do this?
No, absolutely. I think missing value imputation is a very. I mean, there could be an entire course on how to impute the missing values. So I'll try to shed some light. And today, anyway, we are just looking at the overview of the different important components of the data pre-processing. Definitely, we'll come to the missing value and we'll discuss in depth. Okay.
Okay.
So yeah, I'm just going a bit bottom up. Never mind, but we'll touch upon each and every aspect. Today. So. FIRE is an algorithm for detection of rare entities, and let's see how it works. What it does is, these are the data points. Don't get carried away by the notations here of the different colors. So these are basically the data points. You can think of them as data vectors, right? A record. Okay. So with some value, let's say you have 3 features, and the value of these 3 features are following, right? In this way, you have another data point, another data point. So you have many such data points, and some of these data points are in plenty. If you just, so these colors are of course not known, right? This is, in this paper, we talked about the different cells. Each cell is a numerical vector, and if they are in majority, then of course it's fine. But if they're in minority, then so for example, these black cells are in minority, right? So they're rare cells, or they're outlierish data points, right? I mean, so in this algorithm does not really discriminate between the rare and the outliers, but it's pretty much it works for even rare cells. I mean, outliers, they are both, I'd say. So the way it works is it uses a concept of big data algorithm. It's called hashing. So just let me give you a bit of an idea of how the hashing works. Primarily, there are different hash families. So let me talk about the locality sensitive hashing. The overall idea, I just don't want to take you into the significant mathematical aspects, but simply it's you have some data points. Let's say these data points, you can see they're forming cluster, but in a high dimension. So this is of course 2 dimension, right? This is dimension 1, this is dimension 2. But the moment this dimensions increase to, let's say, 1,000 dimensions, we cannot view the data like this, right? It becomes a lot more difficult. So what, and of course, finding the nearest neighbors, so for example, if I have a new data point, I want to know who are the nearest neighbors. It takes a lot of time, because you'll have to scan all the data points and see that which ones are the nearest. So nearest neighbor is such an important method. I don't know whether you have heard of this. Anybody among you who have heard of the nearest neighbor? Yeah. Anyone among you heard of nearest neighbor method?
Yes, sir.
In what context?
I guess KNN.
Yeah. So nearest neighbor is a very fundamental concept. It's not only used in the classification. It could be used in clustering. It could be used in outlier detection. It could be used in a database search, right? You want to find out, for example, somebody had applied for a credit card. Now you want to see that who are the similar customers, right, who applied for with the different values of the fields that are typically captured in the record. On the basis of that, let's say you want to understand who were these 10 similar customers that that applied for credit, and what was the decision, right? So it has multiple uses, like classification, clustering, right? We, for the first time, showed it could be used for outlier detection also, right? These are different data mining problems. And it can be also used in database search, right? And all that. I mean, pretty much everything in machine learning can be, there you will always find some algorithms which use nearest neighbor. But it's actually pretty complicated, right? Nearest neighbor means it might sound to you like very easy, like you compare the interior distance for a given data point with the rest of the data points and see that which ones are the closest. But it's time consuming, because if you have millions and billions of records, then even scanning each and every data and computing the distances will take you a lot of time. So I don't know whether you have heard of this guy, Rajiv Motwani. So he was the mentor for Sergey Brin and Larry Page of Google in Stanford. He's one of the founders of big data algorithms. So for the PageRank algorithm, he was the mentor for these two guys, right? And he died in India like a few years back, drowning in swimming pool at his Kashmir house. Anyway, so he came up with the concept that if you just draw some random hyperplanes, let's say I draw 3 or 4 random hyperplanes, cutting my data randomly, of course, in the space in which the data lie. Then, if you simply use these hyperplanes as so for example, if you have 1,000 dimensions and you decide to draw only 10 hyperplanes, right? And what these hyperplanes will do, right? These hyperplanes will be used as yardstick of whether your data is on the left hand side or the right hand side. Oh, okay. So, for example, if I have like data point 1, data point 2, and then hyperplane 1, 2, 3, hyperplane 1, hyperplane 2, hyperplane 3, hyperplane 4. So what you are doing is basically you are looking at each data point and asking whether it is on the left hand side of the hyperplane or the right hand side of the hyperplane. That means you are taking a dot product of the data. See, this Microsoft does this weird thing. They try to extrapolate some smooth shape out of. Okay, so let's say this is data point versus hyperplane. And if the dot product gives you greater than 0, there's the right hand side, less than 0 is on the left hand side. In this way, you can actually give a binary code to each of the data points, right? And it turns out that, and of course, this is a completely random operation. This is a random matrix multiplication operation, right? This hyperplanes are random. That's why I'm calling it random, right? So that's all you are doing. And you can imagine if you use GPU, for those who know, GPU can really accelerate your matrix operations, right? So it doesn't take any time for you to consider some random hyperplanes and projecting the data into a binary bit space. So I'd call it a bit space, right? Because these are bit strings representing the data. Now you take this data point 1 and data point 2 and measure the Hamming distance. The Hamming distance, is very simple. For example, if I have 0, 1, 0, 0, 0, 0, 1, 1, then my Hamming distance is 3 here, because this, and this are all different, right? So out of 4 is 3. So 3 becomes the Hamming distance. Now it turns out that the Hamming distance in the binary bit space actually approximates the cosine distance in the original space. Now here you stop for a moment and see how exciting is the result. So what it says is, if you have a Hamming distance in binary space that approximates cosine distance in original space. Okay, so that's a massive result, right? Because essentially you are.
Guys, I take a pause here. Did you understand what is explained in this particular part of the lecture? So we are trying to explain an approximate method for finding out nearest neighbors at a very, very fast pace, okay? Through a lot of random operations, random dot products and matrix multiplication operations. And let me tell you guys that that finding nearest neighbors is a very, very crucial component of data science. It has its use cases in multiple scenarios. You can do a classification using nearest neighbors. You can do a clustering using nearest neighbors. So that is a fundamental block of machine learning that is used by multiple other algorithms as part of them. And nearest neighbors is not an easy task to perform. So if I give you a bunch of 1 million data points, in order for you to find the nearest neighbors for every data point, you will have to have an adjacency matrix. All by all distances have to be computed, which is a quadratic complexity. Even if you humor the complexity of finding the distance, depending on whatever is your distance method, the very complexity of constructing the matrix of all versus all distances is huge. You can imagine, right? 1 million by 1 million is a huge matrix. And if you don't compute the all versus all distances, you can never get the exact idea about who are the nearest neighbors of a given point. Is that making sense to you? So here is a method, locality sensitive hashing, that allows you to find approximate nearest neighbors very, very rapidly. A lot of times, you don't need to find the exact nearest neighbors. Okay? For example, in a credit card issuing company database, right? Let's say ICICI Bank. So when you ask for a credit or a loan, right? A customer asks for a loan, you want to check that whether such customers, not that customer is asking for a loan for the first time, but customers who were similar to this person who is asking for a loan, whether they paid the loan back in time. You see, whether they paid back the loan in time, that's the question you are asking. And for that, typically these company databases, these banking databases are very, very large, like tens of millions of records they will have in their database, right? Transactional database. Now you don't need to know who are the nearest neighbors. You want to do a very quick decision. You don't have days to find out the exact nearest neighbors, but if you can get some approximate nearest neighbors, you can take a call. You see the point? So there's a massive, I mean, without this algorithm, big data mining does not exist to me. It's the most fundamental contribution by an Indian American, and you should learn about it more. Okay? And what this method does is simple, very, very simple, that it takes the data, right, and draws multiple hyperplanes in random directions. And then they simply see for every data point whether it is on the left hand side of a hyperplane or the right hand side of the hyperplane. Accordingly, it codes the data, right? So it is coding the data as per that, right? And this can be done using dot product, because this is also a bunch of values. You can just replace. There's an equation, right? There's an equation, a straight line equation, you can imagine, and you can plug in the value and you can see whether it is the right hand side and the left hand side, and then you can come up with a bit code like this for every data point, and you can measure their Hamming distance, right? And so just imagine what is happening here. If I give you a very large database, okay, like 20,000 dimensions and 10 million data points, all right, so you don't need to find out the adjacency matrix. Okay, so your data, you don't need to find out the adjacency matrix between the data points to find out their distances, pairwise distances of the data point. What all you need to do is you need to encode, you should come up with a bunch of these straight lines, and you should multiply them with you should find the dot product of that with the data point. And that gives you a binary code. And this takes minuscule time. It doesn't take any time. If your data is in a matrix form, you just multiply with another matrix of this, of the hyperplanes, and then whatever 0, 1 you get, based on that you can come up with a binary coding. So it is very easy. Okay, and then you can imagine that this is kind of a crude representation, crude dimensionality reduction for the data. Even if you have 20,000 different values for a data point, you are representing that by just 4 digits, that too are binary. Now what will happen is a lot of data points will share the same binary code. And interestingly, according to the mathematical proofs that have been presented as part of this work, it suggests that if the yeah so the if a code is a binary, if a binary code is shared by the data points, they are nearest neighbors of each other. So for example, if you look at here, they will have the same binary codes, right? Because they are at the same side, on the same side of the hyperplanes. They'll have the same binary codes, isn't it? These two data points. But did you draw it in this way, taking care of that? No. It randomly so happened that these two data points are at the same side of all the hyperplanes. For example, you could have drawn a hyperplane cutting through this cluster. That's fine. But those instances will be very less. So your overall having distance between two data points that are nearby will be very small. You can visualize this algorithm by imagining that all of you are in a room, right? And in a very big room, and you are creating small clusters based on who is friend of whom, right? And you're just talking to each other, right? Having some drinks, for example. Now all of a sudden, that room is randomly divided by some walls popped up in randomly and connecting two ends of the room, right? So what is the chance that, how unlikely you can imagine it will be to get detached from your friend whom you are talking to? It will be very unlikely. Whereas if you are far off from a cluster of your other friends, then you are almost certainly going to have a different bit code, a different configuration of the walls around you as compared to your friends who are far off. And it is very likely that you will have a similar configuration of walls for a friend that you are talking to. And therefore, you may end up in the same cubicle. So the room is getting divided into cubicles. The chances are very high that people who are talking to each other fall in same cubicles. One or two walls might cut you across, but those instances will be far less, likely than the instances where it's completely different cubicle. It's very different, right? So that's the original idea of locality sensitive hashing. And this is what has been used in the work that I'm describing here. Okay, carry on, guys. So do you have any question? This is important material for data mining.
Just I had a question about this. I mean, when you were talking about this, you mentioned about random hyperplane. I'm just trying to
Yes.
I mean, is it really random, or there has to be something? I mean, say for example, like what I'm trying to understand is there are data which is having maybe 10 attributes. So in
It's
that case,
completely random. It's completely random. If you have 20,000 features in your data, 20,000 variables, then it is a 20,000 variable space, right? If I have three dimension, there is a three-dimensional space. If I have 20,000 variables, this is a 20,000 dimensional space. Now, you are saying this is a very high dimensional data, but I will just draw 10 hyperplanes. And interestingly, these 10 hyperplanes will be drawn in random. But yes, you are right. There are many ways of drawing the hyperplanes. Okay, there are they always come from some statistical distribution, but they are random. They are not based on the data. Okay, they don't care what is the data.
okay, thank you. I got some clarity to my question. Thanks.
Or your matrix operations, right? So it doesn't take any time for you to consider some random hyperplanes and projecting the data, telling the Z there are very few data points already existing, right? So essentially, yeah, you can actually measure the Hamming distance, and that will approximate how distant they are in the original space. So that's the concept of the locality sensitive hashing. So if I give you a new data point now, you simply need to multiply the data point. You need to do dot products of the data point with regards to all your hyperplanes, right? And hyperplanes are predefined, so that will immediately tell you the zip code of the data points which are similar, which look similar, right? So you will immediately land it in this particular cubicle if the bit code of the new data is shared, is the zip code of the cubicle, right? Or of the city, which so the mapping becomes very efficient and fast. Okay, so I think that's the overall concept. You need not to, worry about the precise mathematical proofs or the convergence or approximation proofs or anything like that right now. But if one of you is interested, please check out Rajiv Motwani's works on locality sensitive hashing. It has now become dated. People use sketching and other algorithms for it. So essentially, it's a very rapid nearest neighbor finding algorithm, right? Now, what we do here is something similar. We take a very large cohort of the data points, and then we draw hyperplanes, some random hyperplanes, and we draw a set of random hyperplanes multiple times. So, for example, I decide to draw 10 hyperplanes, but multiple times. It's like bagging or boosting, right? And why I do so? Because I want to factor in the different kinds of biases, right? Because of the wrong choice of the hyperplanes or some other reason, you might get your approximations might get distracted. So you just do it multiple times because it's very rapid. It should be, you can check the code, right? It's free. Now that means what? Of course, I told you, don't think that the colors are given to you. It is just a notional abstract art, I would say, just to explain how the method works. So what happens is that all these cells here are the data points, and then we draw sets of random hyperplanes multiple times, and each hyperplane will give kind of a column of cubicles, right, which are different binary hash codes, and multiple data points will be assigned to this hash codes or the zip codes, right? And multiple rooms could be free also, vacant, right? Like in our example, this room is vacant. So not necessarily every room will be occupied by one or more data points. So now we use now imagine what will happen is that the data points which are rare, they will typically be mapped to a room where there are very few data points already existing, right? They will be part of a crowd. They will not be, if it is coming from a space where there are very few data points, then they will not land in a cubicle where there are too many data already there. Okay, so that's the idea. So we can very rapidly compute the probability. So we assign the same probability. Like you can see 0.32 is the probability here, 0.38, right? So that means the probability of landing in that cubicle is 0.32, which is the number of points in that box divided by the total number of points is how you compute that, okay? That's how you compute it. And of course, and you assign that probability to all the data points which are allocated in, which are assigned to that particular cubicle, okay? And you do that multiple times, then there is a method called Fisher score, okay, Fisher's method, which basically pulls. Now what is happening is for every data point, you have multiple probability values. Probability 1, why this is, yeah, probability 1, probability 2, probability 3, and so on and so forth. And all these probabilities values are pulled together in a way. If you look at this particular equation, this is called Fisher's method. What it does is it combines the probability, right, with this formula, right? So the rare ones will end up getting very high score because of the log there. What will happen is the rare ones will get a very large score, and the ones which are abundant will end up getting very small score, right? So it's in a way giving a rareness score to the data, and it's very fast. It's completely, it can beat any algorithm.
Guys, do you understand what is happening here? So some data points are given, right? And the different colors here are meaningless, because that just explains to you that they are of different categories. Okay, they are similar within themselves. They are the implicit classes which are not shared with you. Now what happens is, these are high dimensional data points, and you sort of draw random hyperplanes, multiple sets of random hyperplanes, and depending on how many data points land in a particular hash code, which is marked as a cubicle here. A hash code, a unique hash code, is a cubicle. Once you draw random hyperplanes, you get multiple cubicles. You have multiple cubicles, again multiple cubicles, right? And depending on how many data points you land in one cubicle, divided by the total number of data points, is a probability that you can assign to all the points in a given cubicle. So every point within this box will have the same probability. That is the number of points in this box divided by the total number of points. And that you want to do in all the cases. And when you do that, you get, for every data point, multiple probabilities. It is kind of a bagging approach, right? So you draw the hyperplanes multiple times, so you get multiple probability values for every data point, and you can combine the multiple probability values like this. You will get a large, so what will happen is, a rare cell, for example, you see this cubicle, black cells are rare, black data points are rare. So it happened to be the case that the cubicles where the black cells landed have very few cells inside. So the probability attached to this is much smaller, as you can figure here from here, 0.02. So only 2% of the cells, so 2% of the data points landed in this cubicle or ended up having the same binary code. So now you can multiply, you can sort of take the log of the probability and sum them up, and using this formula. This is a Fisher's score or Fisher's method. So we call it fire score here because so we don't know the distribution of this particular statistic. This is a statistic for which the original distribution is the chi-square distribution. But since we are coming up with the values in a different way, right? So we don't expect it to follow chi-square distribution necessarily, but we don't need that at the same time. All that we need is a way to combine the probabilities. So this formula will give a higher probability of a rare cell, a rare data point. Okay, so that has been shown here. And this algorithm is massively fast. No algorithm can beat it. Okay, so this is a paper that we published in 2018 in Nature from our group. You can check it out. It will be a good read, at least the method part of it. The other rest of the parts you will not understand.
I mean, of course, now professionals for underwriting the loans, that individual or the business at any place, if there's, and so on and so forth, right? All these things taken together, you create a report basically in the end, right? And so the details here on the left hand side. You can also go to my web page and get hold of it. Okay, now let's move forward. So what do you do? Let me start from the beginning now. That what do you do when you have encountered a data? Okay. So typically you start with data aggregation, right? Typically you start with aggregation of data from multiple sources. And I already gave you a few examples last time. Like I was working for a fintech company where they underwrite the loans applied by small business owners, and therefore they cannot maintain a very large team with highly paid professionals for underwriting the loans, and therefore they just automated the process through NLP, right? And they curate data from different places like Yell.com. Yell is a place where typically, you will find reviews by consumers for different businesses, right? Business reviews, and then you will have Facebook and Twitter, because every business will have a Facebook and the Twitter page, right? You can see their fan following. You can see what sort of complaints people have raised. You can also look at justice.gov, right, where you can find out if there is any legal proceeding that has been carried out against that individual or the business at any place. If there's and so on and so forth, right? All these things taken together, you create a report basically in the end. And of course, a lot of machine learning is involved in this whole thing, and it works very efficiently. So you can imagine the first thing that you'll have to do, and of course this is not taken care, this topics will not be taught as part of data mining, but always remember that machine learning and data mining is only the tip of the iceberg. It's the tip of the iceberg. The real chunk of ice is very different, where you need to understand the domain, you need to set up the data warehouse, where the different pipings and all these things will happen. And after the data warehouse is created, then only you can create multiple views of the data and then do data analytics. The commonest platform is, for example, SAS, right? And SAS has all the modules for data warehousing or data, in fact, SAP also has Oracle, right? PeopleSoft, all these companies have their own database management system and the data warehousing facilities and the infrastructure, right? So that's where you get started. And that, of course, as a data scientist, you typically don't take care of that, but depending on the organization you're applying for, or you at the time of searching jobs, you may end up, getting a position in a company, a startup, which expects you to do even data warehousing by yourself, right? And there you'll get into trouble. So this role is called data engineers, right? Data engineers. And data engineers will typically do the warehousing, and after that, the data scientists and the machine learning engineers will create models and productize. So that's the first thing, that's data aggregation. After you have aggregated your data, you'll have to look for the duplicate values. You can remove that. You'll have to look at the missing values and remove that. Now, missing values can be handled in multiple ways, right? The commonest is, if you have a matrix like this, and if you have too many missing values in a particular row or a particular column, you typically can discard it, as long as it does not amount to discarding too many of the rows and the columns. And a column is a feature, right? So removing a feature altogether might be a little more threatening. However, if you don't have dearth of features, if you have many features, you typically don't care much for dropping one or two in case they have excessive amounts of missing values. And the same applies to the records, the data points, where if you have too many of missing values, or the null values or NaN values, it typically occurs in NaN, Na, right? Or, in some cases even 0. You'll have to be careful, like which are the missing values in your data. And of course, you can drop all these rows which have excessive missing values without bothering much if they are not in plenty. Like if you have only 2% of the data with excessive missing value of, you would probably drop them and go ahead with the rest, right? But in case that's not true, then you run into problem, because then you have to fix. There are many methods. The most rudimentary methods, however, well-used methods are, replacing the missing value by mean. When I say by mean, that means you look along the feature direction, right? So for example, here you have a missing value, here you have a missing value. You take the mean of all the features and you you take the mean of the values for the features, and then you impute the missing values with that. The other could be median. The other could be some robust medians, which actually ignore the outliers, etc. Right? So they're robust median or mean, whatever. There are different robust methods, robust statistical methods, which essentially ignore the outlierish values along the features. Okay. So that's pretty typical, I would say. But then there are other more complicated methods. One very useful method is multiple imputation using chained equations. chained equations. This is one of the most famous standalone. Yeah, this is called mice. Just remember this. It will be really helpful. So mice actually uses regression in form of expectation maximization. Now, these words might sound a bit complicated to you. So what they do is they try to predict the basic values from the data where the values are not missing, right? And they do it in repetition. So because what happens, let's say, okay. So let's say there are, for one feature, there are two values which are missing in this direction. So they will first, you'll have to read the algorithm from the paper. It's a research paper, you can just read it. But what they do is they predict the missing values using regression from the rest of the data points. Like if these values are this, then what should be these values from the data where, where there is no missing value. They use those data to predict what will be given. This is the value for this feature, this is the value of this feature, what is the value for this feature, right? So they pose it as a regression problem. And then they repeat it, because then they consider, okay, now whatever you got as a regression, you treat that as the real value and then try to impute the other missing values, right? In this way, circular. And if you have learned k-means, they do something very similar, which is broadly termed as expectation maximization. So they do multiple regression, and therefore it is a bit slow, in fact. Okay? There are other methods also which look at k-name, nearest neighbor again. They look at similar data points and then they take the mean or the median of the values of the missing value from them. So for example, if you have this kind of data, let's say, I'm just drawing them in a low dimensional plane. If you have this kind of data, and then there is, let's say here you have a data which has one missing value in one of its features. What it will do is it will find out the nearest neighbor and then try to, instead of taking values from everyone, because when you replace it by mean of all the data points, then it is misleading. Instead, you can just consider the mean of the data points which are actually very close by. Okay, this is a simple strategy that in a way it makes sense. All right. So there are many methods. I just gave you some basic ideas, and at the time of application and practice, you will see and use some of these methods, I'm sure. Okay, outlier detection also we have discussed, because as I told you, sometimes it is better to remove the outliers, before performing any kind of a learning task, so that it is not biased due to the outlierish data points.
So guys, I think I will stop it here. There's too much of things shared in this class. So for the next 2-3 minutes, I'm open to have any question. And after that, you can just break out and come back on yet in this class. We will not have that half an hour lab today. It will kick in from the next time. There is nothing that we should do in the lab today. So you can just ask me if you have any question in any of the topics that are. I will share the links of the videos. I'll set up the page also for the data mining course in the Google Classroom. So we talked about data type. Yeah, tell me.
Sir, you mentioned about 2 books. I think if you can,
yeah, so these 2 books are Han and Camber. Please ask the librarians to supply these books, okay? Han and Camber and Vipin Kumar, Introduction to, but I think this book, Vipin Kumar's book, or both the books, you can actually buy for yourself. This is a good collection, I would say. You'll get it from the library in any case, Introduction to Data Mining. This is also something like that. I don't exactly remember. And also you should check out Vipin Kumar data mining website. I think they have a very good, yeah, so they have a very good website accompanying the books where you'll have a lot of slides. Um, I will pretty much follow this book, with a few here and there changes, new algorithms, because this is slightly old school, quite basic in nature. I may teach some new stuff. They have a lot of Python notebooks as well. So you just go and check them out. Like for every class, they have a. This is a great practice for you guys. Introduction to Python, introduction to NumPy pandas. It's a very authentic source, for data mining. Yeah, so you can just download this and um, use it. This is the tutorial. It's good to just run these things, right? And we'll practice all this next class onward. All right, guys. So any other question? Books, please write to Rajendra of the library. He's very helpful. Anything else in the? Okay, by the way, so one more thing is that you you can read this article. I discussed about our algorithm Fire. It's I mean, currently I think it is the best algorithm for outlier detection, and we are proud to have this out of our group. So I request you to study that. I'll For the time being, I'll put it on the WhatsApp group. Okay. So later on, I'll put everything together. Maybe tomorrow. So at least the method section you can study from here, because I have started teaching this algorithm in the curriculum, right? Because it's the best right now. And there is another method we'll learn, local outlier factor and HBOS. Those are also very rapid and quite good, but ours is better in accuracy. So anyway, so check them out, and let us come back and discuss in the next class. Thank you, guys. I'll share the class links and everything on the recording. Have a good day. Bye.
Okay, thank you.
Thank you.